Hello, good morning, good afternoon, or good evening, wherever you may be. Welcome to today's webinar hosted by AC Kalkitech. I am Midun from the marketing team at Kalkitech, and today we'll be discussing on an interesting topic, one that has been asked by many of our customers and partners. Today we are going to discuss about performance benchmarking for meter head-end systems through large-scale meter simulations. The webinar will delve deep into how to evaluate and optimize Meter HES solutions in real-world conditions and evaluating for performance criteria like scalability, reliability, and resilience. A couple of hygiene points before we start off this webinar. This is going to be a 45-minute session and will be followed by a 5 to 10-minute extra for Q&A. Also note that this is a listen only webinar. If you have like any, if you have any questions or any query, please feel free to ask on the chat window. So you can ping me, shown as AAC Kalkitic Marketing, and I will consolidate all the questions and have it answered towards the end of this webinar. In case we are not able to answer every question, we will definitely get in touch with you personally through your email and try to answer all your queries. Also, this is a webinar that will be recorded and will be sent to all the attendees today. Um, which will be sent in a day, 24 to 48 hours time. It will be automatically sent to your email ID. Also, we will be emailing a webinar participation certificate to all the attendees today. All right, I see a few more folks joining in. Let me take this time to introduce our host for today's session, Aparna Regunath. Aparna has many years of experience working in smart metering and communication and works in our key metering services division at Calcitech. Her chief interests are design and implementation of DLMS protocols solutions, consulting, and training in DLMS COSM, etc. And she's taken various training programs for organizations like CPRI, PGCIL, KSCB, etc. She is also an active participant in the companion specification design for numerous utilities, including PLN, Meralco, PEA, etc. All right, so let me hand over the mic to Aparna. Aparna, over to you.
Thank you, Midun. Hi, all. So, now we'll dive into our topic for today, performance benchmarking for HES through large scale meter simulations. We'll also discuss why performance evaluation is required and how it can be performed. So, let's get started. Firstly, let's start by understanding what do we mean by the term Meter HES performance benchmarking. The HES performance benchmarking is a process that helps us to evaluate the efficiency and effectiveness of our hidden systems in managing and processing the data from smart meters. That is, if we are considering a smart grid network with millions of smart meters communicating with our hidden system, as illustrated in the image, how efficiently can our HES manage and process the data is analyzed through performance benchmarking. Now, the next question that you would be having is why performance benchmarking is mandatory or why do we have to perform performance benchmarking? Let's now understand the need for performance benchmarking in detail. When we are considering a smart network where we would be having millions of meters communicating with our hidden system, there could be scenarios like power failure occurrence, voltage sag, surge, or overcurrent happening. Hence, it's very important that we evaluate the stability of our electrical network, how the system responds to these unexpected scenarios. Here comes the first application of performance benchmarking. It helps us to identify the potential threats that could happen in prior to the HES commissioning or installation. The second application of performance benchmarking is to monitor the communication success rate. When we have a large number of meters communicating simultaneously with our headend, there is a probability that majority of the meters might fail to communicate with our headend system. And by performing scalability testing, we can evaluate the communication success rate or what percentage of the meters can successfully communicate with our headend system can be estimated with scalability testing. Now, coming to the third use case, which is to monitor the key performance indicators. To understand this in detail, let's see what are the key parameters that we need to consider while evaluating our head-end system. The first parameter to be considered is the data collection efficiency. Here, we will monitor the read success rate or the percentage of successful data read from meters and the data collection latency, which is the time taken to collect data from meters. The second key indicator is the data processing capability, under which we will monitor the amount of data processed per unit of time and the data aggregation and storing time. The next KPI is the scalability of the system, which is the number of supported meters that can be handled efficiently, included with the ability to scale resources based on the load requirement. The fourth performance indicator to be considered is the reliability and availability of the head-end system, which will estimate the percentage of time the system is operational as well as the fault tolerance, which is the ability to handle and recover from failures or system instabilities. Moving to the last KPI, which is the security of HES, where we will be considering data integrity and the access control. So we have the data collection efficiency, data processing capability, scalability, followed by reliability and security, constituting the 5 KPIs for a metering head-end system. And by benchmarking, we can understand the efficiency of our head-end system against each of these KPIs. Now, let's head to the fourth reason as to why we require a detailed performance examination. After once we analyze the KPIs, scalability, and potential risks associated with head-end system, we can optimize the head-end to meet our specific requirements as well as ensure maximum efficiency by fine-tuning the head-end. So the fourth reason why performance benchmarking is required is to optimize the performance of head-end system, ensuring maximum efficiency. With these points that we have discussed, you can see why performance benchmarking is critical or crucial to be performed prior to the commissioning. But now comes the next challenge. How do we perform the evaluation of head-end system? How can we mimic an actual environment where we would be having millions of meters? How can we expose the HES to actual scenarios that it would be exposed to after commissioning? How can we perform disconnect control, events and triggers, or firmware upgrades on a mass scale to test the performance of the head-end system? Here comes the role of our AC DLMS million meter simulator, which helps you to evaluate the performance of your head-end system by virtually simulating millions of meters. To understand more, let's dive into the key features of the million meter simulator. The AC DLMS simulator helps you to identify and eliminate the potential threats that could happen in the future to your hidden system before commissioning it. The second important feature is its ability to create virtual meters of any companion specification according to your requirement. Meters of any companion spec can be designed with the simulator. Next comes its capability to communicate using TCP, UDP, or HDLC protocols with support to IPv4 and IPv6 modes of addressing. Followed by that, the tool offers to test the scalability of your hidden system by estimating the communication success rate when we are communicating on a large scale. Another important highlight of the application is its user friendliness. You can very easily get started with the simulation of meters with the simulator. Let's see how this can be done. We'll have a walkthrough of the simulator application now. So this is the simulator application. You can see the UI has been designed in a very simple manner so that you can easily get started with the tool. The first step to get started with the simulator application is to create a new project. For this, let's go to the new option over here. Here, we can input a project name of our choice. Let it be sample. In the next field, we can select the path where we need to save this particular project so that anytime after on, if we need to access the project, we can open it from here. After these inputs are given, we can click on the OK option. And now you can see the first step of creating the project has been completed. Our project has been now saved. The next step is to map a meter template to this project that we have just created right now. For this, we have two options to choose from. The first option is to choose a meter template from the existing meter templates available in the meter templates pane or meter templates library. So this is the meter templates library. The existing templates are available here for our use. Suppose if we are going with one of these existing templates, all we have to do is just drag the template to the project, assign an IP address, and then we can start the simulation. But if we require a meter configuration with a different number of associations or with different security policies or different set of objects, in that case, we can create a template which matches our requirement by going to the template editor over here. A template is basically an XML file which includes all the details related to the meter that we are going to configure, number of associations inside it, its corresponding security policies, along with the different interface classes that we would be requiring in our meter implementation. The first step to create a template is to click on this add association option. Let's click on the add association option. Here you can see we have support for version 0 to version 3. Let's go with version 1 for the time being, adding our first association. Now we'll add a second association by clicking the add association option under version 1 itself, adding our second association. Now, if we go to this partner's ID and expand it, you can see the client ID for the first association is given as 16, which points to that of a public client that we would be having inside the meter. If we are going to the second association, the client ID is given as 32, which points to that of a meter reader that we would be having. So according to each association that we add on, The client IDs will be automatically assigned by the simulator. It can also be modified according to our requirement. Next is the application context name. Here we have two options. We are deciding how the data has to be sent by the meter. If we want it to be encoded, we can go with LN with ciphering. If we want it to be plain, then we can go with LN without ciphering. For the first association, we'll go with LN without ciphering. And for the second, let's go with LN with ciphering. Next is the authentication mechanism. Here we have support for all the authentication mechanisms from the lowest to high level security mechanisms up to HLS 7. For the first, we'll go with lowest, and for the second, let's go with a higher level security this time. Let it be HLS 5 GMAC. The next step is to map security objects to these association objects that we have created here. We are going to add IC64 objects to our association. Here we can choose between version 0 or version 1 according to our requirement. Going with version 0 right now, and below if we expand this drop down, you can see we can choose security policies from the lowest or no security to high level security policies like authentication and encryption. For the first, we'll go with no security, adding it and then mapping it to the first association. Now coming to the second association, we'll create a new security object this time with security policy. Let it be authentication and encryption. We'll go with a higher level security policy. Below, you can see the keys which will be used for communication with the client. These are the default keys. It can be modified according to our requirement. Adding the second security object and mapping it to the second association. Now, we have created a very basic template with association and its corresponding security policies. The next step is to add on objects or IZs to this template according to our requirement by going to this add object option. Here, if we click on the drop down, you can see the wide range of interface classes that are supported as per the DLMS standard. We are starting by adding one IC1 data object. We can give the OBIS code here according to the standard. Now, we'll consider a scenario wherein we are simulating a large number of meters and we need to uniquely distinguish each meter that are being simulated. The only way to do this is by assigning a unique serial number for each meter that are being simulated. And this can be easily done with the simulator, changing the value type as visible string and simulation type as serial number. Here we can give a default pattern, a fixed string followed by two wildcard characters which will keep on incrementing with each meter that are being simulated. So the first meter will have serial number 0, the next 1 and so on up to n number of meters that we are simulating, ensuring that every meter is assigned a unique serial number. Adding our IC1 data object. Next, let's discuss the constant simulation type that is offered. This simulation type is useful for parameters which requires to be maintained a constant throughout the entire simulation period. So for those, we can go with the constant simulation type. Next, let's move on to the IC3 register, giving the OBIS code here. We'll try adding a voltage register this time. Now for parameters like voltage or current, their values have to be maintained between a particular threshold range or boundary limit. And for those parameters, we can go with the simulation type as step. Here, we can give a minimum value, let it be 210 volt, and the maximum value, let it be 240 volt, giving the period as 1 and step as 1. What happens here is that once after we start the simulation, the register starts from the minimum value 210 volt, and every 1 second, as the period configured here is 1, it will increment by a factor of 1. So after 1 second, the value will be 211 volt and so on until it reaches the maximum value 240 volt. Once it reaches the maximum value, it will decrement backwards again by a factor of 1 every 1 second to reach back to the minimum value 210 volt. And this continues as a cycle, ensuring the value never goes beyond the min and maximum ranges that we have configured for that particular register. So for those, we can go with step simulation type, adding our voltage register. Now, we'll add a frequency register. For frequency also, we know that we have to strictly abide according to the tolerance limits to ensure the value never goes out of synchronization. So we are going with step simulation, giving the minimum value as 49 Hertz and max value as 51 Hertz. So here also the value of the frequency register will be maintained between this boundary limit or threshold ranges that we have set for the particular parameter. Adding our frequency register. Next, let's discuss the step with spike simulation. This is pretty much similar to step simulation. The only difference here is that at random intervals, the values of the register or the parameter will go either above the maximum value or below the minimum value to induce scenarios like a sag or surge which could happen within the network. So to induce such scenarios, we can make use of the step with spike simulation type. Then we have the cumulative simulation type. This simulation type is useful for parameters like energy registers or demand registers, which has to keep on incrementing once after we start the simulation. So here we can set a minimum value, and after we start the simulation, it will go on incrementing from this minimum value that we have configured. Next, let's head to IC4 extended register. The configuration is very much similar to IC3. The difference here is that we have a subtype simulation offered called as the maximum demand. And the maximum demand period is given as 900 by default. It can be configured according to our requirement, and the minimum value is 0 and maximum value is 100. These are also configurable according to our requirement. Now here what happens is once after we start the simulation, during this 15 minutes or MD period that we have configured, the value of the IC4 will be constantly monitored, which will be ranging between 0 and 100, and the maximum value that is attained between 0 and 100 during the 15 minutes will be recorded as the value of IC4 extended register. And the time at which this peak value was attained will be recorded as the capture time of IC4 extended register. Next, let's head to the clock object. This object is added so that we get time related information for each data that we obtain from the meter. Adding our IC8 to the meter template. Next, let's discuss the IC7 profile generic object, giving the OBIS code here as per the standard. So until now, we have been adding objects to our meter template. But what if we need to monitor the value changes that are happening to our set of objects periodically? In that case, we can make use of IC7 profile generic object, under which we can add a list of objects which we wish to monitor, and periodically we'll be able to get the value changes that are happening to our set of objects. Let's see how we can add the objects to be monitored. Going to the capture objects field, here on the left side, we have all the ICs that we have added until to our meter template. On expanding, we get to see the attributes under each ICs. We can choose the attributes that we wish to monitor. Suppose if we want to monitor the time attribute under IC8, we can drag this attribute to the right side. Now we'll add the value attributes of IC1 and IC3 registers, summing up to a total of 4 capture objects which we have added under IC7, adding our capture objects. Next is the capture period field, which by default is given as 60. We can change it according to our requirement. Now, if it is 60, what happens is every 1 minute, we'll be getting an entry added to the buffer, which indicates the value changes that are happening to these 4 objects over that 1 minute. If we increase it to say 900 seconds or 15 minutes, we'll be getting an entry added to the buffer every 15 minutes. Next, we have the maximum entries field. Here, we are defining the storage capacity of the buffer. If it is 20, the buffer will be storing a maximum of 20 entries. If we increase it to say 200, the storage capacity of the buffer will be increased to store a maximum of 200 entries. And once after the maximum entry limit is reached, older entries will get cleared from the buffer in a first in first out manner, adding our IC7 object. Next, let's discuss the different capture types that are offered under IC7. First is based on capture period interval, which we have discussed already, wherein we can specify a capture period. And based on that interval, we'll be getting an entry added to the buffer periodically. Second, we have the triggered by event capture type. Let's say if we have added a current register as a capture object, and if an overcurrent event is happening, as and when the event happens, we'll be getting an entry added to our buffer which indicates the value changes that have occurred when this overcurrent event has happened. And after analyzing the value change, we can take necessary actions to bring back the value to the expected normal ranges. The third capture type is based on single action schedule, which is useful in the case of a billing profile, wherein we would be wanting the entries to be generated on a monthly basis. So we can add a scheduler object with the execution time to repeat maybe on the first of every month. And if we have added a demand register as a capture object, on the first of every month, we'll be getting an entry added to the buffer which indicates the demand consumption of the user over that 1 month. And followed by that, we can bill our customers based on the rate of demand consumption. Moving on to the next interface class, which is the IC40 push setup object. Here we have support for both scheduled push as well as event based push. Now, if we're going with scheduled push, we can add a scheduler object here. Going to add a single action scheduler here. Under execution times, if we expand, we can set the execution time. Suppose if we want to give the date as today's date, and we'll give the time as maybe 3 p.m. today. So what happens is today at 3 p.m. this push will be automatically scheduled to happen, and it will happen so without any further manual intervention. The second push trigger is the event-based push trigger. If an overcurrent, overvoltage, or a power outage event happens, as and when it happens, we'll be getting a notification, a push notification, which indicates that a particular event has happened and necessary actions can be taken by us to counter the possible impacts of this event on the stability of the network. Next is the IC70 disconnect control object. Now this object helps us to have a remote control over the meter from the head-end system. If a user fails to pay his monthly dues within the expected deadline, we can change the output state of that user to disconnected so that he remains offline from the grid. And once after he pays back, we can reconnect him back to the grid by changing the output state back to connected. So it helps us to have a remote control over the meter from the head-end system itself. Now we have discussed most of the commonly used interface classes. Next, let's see the event list configuration. Here, if we go to this configuration option, you can see we are supporting all the standard event categories. On expanding one of these categories, for every event, there is a unique event ID that has been allocated to it. So if an event ID 7 is happening, it's pointing to an event over voltage in any phase occurrence and so on for the rest. So for every event, there is a unique event ID which helps us to identify the event. So now we have seen that the simulator supports all the standard related categories. But what if we need to create a custom set of events according to our requirement? This can also be done with the help of simulator. Clicking on the add new event list option, here we can give the event list name as say custom. Then we can add a category to this new event list. Let it be tamper related. To this event category, we can add on events. Let's add a new event. For every event, there is a unique event ID. So let's give the event ID as 301 and the event name as say meter cover opened. So whenever an event ID 301 gets triggered, it's pointing to an event meter cover opened. Adding it, we can add on events to this category that we have created. It helps us to create a custom set of events also apart from the standard used events. Next, let's see another interesting feature of the simulator, which is the profile entries begin time. Now, this feature is useful when we have to simulate entries from a large amount or from a long period of time. So for those, we can go with the profile entries begin time. All we have to do is just pick on this option called configure profile entries begin time. And followed by that, we can set a suitable begin date time. Let's say if we want entries back from 2020. So we can select the year followed by the date. Let it be from Jan 1st, 2020. What happens here is that all the entries from the 1st of Jan 2020 up to today's date will be automatically generated by the simulator so that we'll have a large number of entries or data to analyze from and understand the possible impacts when there is a large number of entries, what are the different flaws that could happen within the network. All of these scenarios can be analyzed with the help of this feature. Now let's see how we can make use of this feature in our case. Here, when we configured IC7, the capture period that we gave was 60 seconds. So once after we start the simulation, we'll have to wait every 1 minute until entries get added to the buffer. To avoid this waiting, we can make use of this feature. Here, we can give the begin date as today's date from say midnight. So all entries from today midnight will be automatically generated by the simulator for you. We'll already have the entries readily available for our use. And this saves a lot of time when we are getting started with the testing process. Now we'll save the meter template that we created by clicking on the save option. Here we can give any name of our choice. Let it be meter 1 for the time being, and the template gets added here to our meter templates library. At any later point of time, if we want to use one of these templates, we can simply drag it from here and get started with the simulation. We also have the option to export this template to the desired location as well as to import templates from a particular location to the meter templates library. Now we'll see another feature of simulator, which is Here, if we go to any of these objects, you can see apart from this configuration option, there is a separate option called as access rights. And here, if we go, for every association, we can select the privileges that we want to set. Let's say if we want to remove the read access for IC3 register under association 1. All we have to do is just uncheck this R option from association 1. We'll do the same for the second IC3 also. So when we are trying to read the data through the public client, the IC3 registers will not be available for us since we have denied the read access for IC3 registers from association 1. So this helps us to set different privileges for different users or different associations within the meter itself. Now we'll save the changes that we have made by clicking on the save option. Next, we'll try to simulate this meter that we have created, going to the project editor over here, and then we'll map the template that we created right now. Now we have to assign an IP address. Followed by that, we can give the number of instances also. Here we are specifying the number of meters that we wish to simulate under the particular IP address. So here if we give it as 2, we are going to simulate 2 meters under this IP. Clicking on OK option. Followed by that, we can start the simulation. Before that, we'll see the different options provided for starting the simulation. Going to the settings option, here under simulation mode, we can choose on-premise or AWS cloud simulation mode for simulating our meters. Now, if you're going with on-premise, the simulation will be hosted in the host network or in the host PC itself. But if you're going with AWS Cloud, the simulation of meters will be hosted in the AWS network. For accessing the AWS network, we can upload a configuration file which will contain the list of IPs to connect to the AWS network. And followed by that, we'll be simulating our meters on the AWS network. Users can swap between these options according to their requirement. Now we are going to go with the on-premise simulation mode. The only difference is where the simulation is being hosted. The rest of the features, configuration all remains the same. Now let's start the simulation by clicking on the start simulation option. We are going to simulate our meters in the on-premise simulation mode. After the simulation has started, we'll see the different advanced control options that the simulator can provide to you. Here we have the simulation summary, which indicates the number of meters that are running. We have simulated 2 meters here or 2 meter instances here. We also have the meter template information and IP information and port information on which the meter has been simulated. Below that, we have a simulation control panel to regulate each set of meters under each panel that we would be having. If we want to stop all meters under this particular panel, we can click on the stop all option. And on stopping all, you can see the 2 meters that we had initially simulated are now stopped. To start it back, we can click on the start all option. So these options were stopping or starting all the instances under a panel. Now, if you want to selectively choose a range of meter instances to start or stop, that can also be done with the simulator. Going to the advanced control over here, the first option here is the instance start or stop. Here we can choose a port range or a specific port of the meter or meters that we wish to start or stop under a panel. Here, if we click on the stop all option, out of the 2 meters, you can see one has been stopped and only one is running. So this feature helps you to induce scenarios like a data gap or power outage that could happen within the network and to test how the HES is able to respond to such unexpected scenarios. To start it back, we can click on the start option. And now we have the 2 meters up. Now we have seen how we can start the simulation with the simulator and how to create a template using simulator. Let's see how the simulation can be done with 1 million meters. So here we have an illustration which shows how we can perform benchmarking of the HES with 1 million meters. Here on the left side, we have the simulator simulating 1 million meters. And out of the 1 million, we have received a success rate of 99.99% of meters are successfully simulated. Each meter is also assigned a unique serial number and a unique IP and port for identification under each panels or under different panels as illustrated here. These are the different panels that we would be having. Now what we are going to do is, we are going to check the performance of the hidden system when we are simulating millions of meters. For this, we are using the Kalki.io platform, which is the HES platform that is offered by Kalki Tech to enable communication with meters on a large scale network. On analyzing the HES, you can see we are able to achieve a good connectivity close to 99% out of the 1 million simulated. So this helps us to estimate the scalability of the network. We have received a good scalability count here with 99% of the meters successfully able to communicate with our hidden system. So from this, we are able to estimate the scalability of our hidden system. In the second widget, we have the data availability trend, which helps us to estimate the data accessibility across different days. We have received a data availability of 99.79% here across the different days that we have considered. Followed by that, we have a polling summary, which indicates the status of each poll on a daily basis. The last is the poll status trend, inside which we get the information related to the time taken for each polling to be done. Usually, it takes around 7 to 8 minutes on an average for each polling request to be completed. So, we get the information related to each polling set here by looking this graph that we have received. Hence, by analyzing these informations that we have received in the HES, we can estimate the performance of our hidden system. Apart from this, we can also trigger events, do firmware upgrades, perform disconnect control on a large scale with simulator, and monitor how the HES is able to respond to these scenarios before we commission it to an actual network. Let's see how we can trigger events with the simulator. Here, we'll use a different template that we already have with us, and we'll see how this has been configured. Going to give the IP address and let the number of instances be 1. On going to the template, we have all the commonly used interface classes added here, and apart from that, we have an event configuration section. Here, if we go, there is an event list which indicates the list of events that we can trigger with this particular meter implementation. To understand more, let's go to the event list once again. And here, if we expand the power related category, 101 is pointing to power failure occurrence and 102 is pointing to power failure restoration. So every event ID is assigned a unique event, and whenever that event ID gets triggered, an event pointing to that respective event ID will be generated or triggered. Now let's go to the event status word. Here we can define the mapping position for each event. And whenever that event gets triggered, the bit position will be set to 1 to indicate the occurrence of the event. Next is the push setup, under which we can specify the destination address, the IP and port to which the push will be triggered. Next, let's start the simulation. clicking on the Start Simulation option. And to see the event trigger, we'll be using the Meter Explorer tool, which is another client that is offered by Kalki Tech to test the communication with your server implementations. So from here, you can see the compatibility of the simulator tool. You can use it to communicate with the head-end system by simulating meters on a large scale up to 1 million, as well as use the same simulator to scale down to the required count that you require to communicate with a small scale client. So the number of meters can be regulated according to your requirement, and it can also be designed according to any companion specification. Adding a meter here, and then we are going to change the IP address type as dynamic IP and the listening port as 5000, which we had given in our meter template. Now we are going to add an association and going to enable push inside it. Now we'll start listening to this particular port that we have configured. Let's start listening to the port set so that we are able to receive the push that gets triggered to this particular port. Going back to the simulator, here under advanced control, we have this option called event trigger. We can specify the port ranges here, and events will be triggered to those mentioned port numbers or port ranges. Now we'll choose an event that we are going to trigger. Let it be event ID 101, going to trigger the event. Now let's go back to the client, and now you can see we have received our first push pointing to event ID 101, power failure occurrence. Next, let's try triggering a second event. Let it be 102, power failure restoration. Triggering the event, and going back to the client, we have received our second push as well, which is pointing to that of the power failure restoration. So by analyzing the push packets that we have received, we can identify which event was triggered and necessary actions can be taken by us to counter the possible impacts of the event on the stability of the network. Now we have seen how we can do a push communication with simulator. Next, let's try doing a pole communication. Here, going to add a meter and going to give the meter IP. The meter IP address is the same, and adding a custom association. Let's try communicating with a public client. Now we are going to do a test configuration. The test configuration is successful, which indicates we are able to successfully communicate with our meter implementation. Now we'll do an object list download for this association. If we expand the object list, let's try checking the event log for voltage related category. And here you can see, according to the events that we had triggered, we are able to receive the information related to the event code as well as the timestamp of its occurrence. So you can simulate events from the simulator as well as test scenarios, whether the event gets logged into the event log. All of these advanced conditions, test conditions, can be virtually simulated with the help of simulator, which helps us to mimic an actual environment for proceeding with our testing. Next, let's go to the block load profile. You can see how the entries gets added to our IC7. We have the capture period as 60, which is why we are getting the entries every 1 minute here. Now, we have seen how entries looks like inside the buffer. But if we have a large number of entries, say if we have thousands of entries and we need to selectively choose only the first 500 of them, in that case, we can make use of a feature called as selective access. In our case, let's say if we want entries only between 2 to 2 p.m. So with the help of selective access, we can give the from time as 14, applying it, and then the to time in 24-hour format as 14 2. applying it, and then doing a demand scan or a get basically to the meter. Now we'll see how the entries are being captured or displayed in the buffer. Going to the buffer, you can see we have the entries only which we have selectively requested for, or only between the from and to range that we have configured under selective access settings. So this helps us to have a detailed analysis to a large number of entries. If we want to specifically analyze only a small set of entries from a set of large number of entries, we can make use of this feature called as the selective access. By now, we have discussed what is performance benchmarking, why it is crucial to perform HES benchmarking prior to the commissioning, and we have seen the important role that is played by simulator to perform benchmarking. We have also seen how we can use simulator to test our HES systems, how to configure meter templates of our choice, perform events and alarm triggers, and disconnect controls, as well as do firmware upgrades on a large scale. Thank you very much. Let's now proceed to the Q&A session to answer the different questions that you would be having regarding the simulator or performance benchmarking.
Thank you so much for the session, Aparna. We do have a few questions that has came in during the webinar. Let's pick up a couple of them. So one of the questions asked was how to test the firmware upgrade on large scale using a simulator.
Firmware upgrade can be tested with the simulator, as we'll use the template that we used here. And let me just show it for you. Here we have this option called add object. And from the drop down, you can choose the image transfer object, adding the object, and then followed by that, we can give the access rights. Here, if we enable the execution rights, after the execution rights are given, we can scale up the number according to our requirement to do image transfer or firmware upgrade on a large scale. We can use it up to millions of meters and see how the HES is able to analyze the different firmware upgrade responses and how firmware upgrade gets completed on a large scale.
All right, great. I have another question. This is regards to disconnection control. So does the simulator offer disconnection control functionality?
Yes, simulator supports disconnect control. We can add IC70 disconnect control object here. And on executing methods like remote reconnect or remote disconnect, the output state here will automatically change. If we execute remote disconnect, output state will go to 0, and on executing remote reconnect, the value will automatically be brought back to 1. So that additional intelligence is also supported by simulator under disconnect control. You can also perform it on a large scale. If we are simulating millions of meters and we have to execute disconnect control on, say, 100K meters, we can execute the commands on a large scale according to our requirement also.
All right, good. So I have one of the attendees asking the couple of questions from his side. One is, can we simulate network delays during the communication? And also the other one is, does the simulator offer support for all security suites?
Network delays can be simulated with the simulator. Here we have an option in the project properties. We have an option called enable network latency simulation. And if we are enabling it, we have the provision to set a delay. We are setting an intentional delay here in the communication process. So if it is given as 120, what happens is every responses from the meter will go back after 2 minutes, or there will be an intentional delay of 2 minutes for every response that goes from the meter. It is useful when we are simulating a large number of meters. We can intentionally set a delay in the communication. We can also go with random network latency, wherein the simulator will automatically assign a latency for you in between these ranges 120 to 300, and that delay will be set for each response that goes from the meter. The second question was related to whether it supports all the security suites. Yes, all the security suites are supported. Let me show it for you. If we are adding a new template and if we go with version 1 of IC64, you can see we have support. If we're going with version 1, we have support for suite 0, 1 and 2. If you're going with version 0, as per the standard, there is support for security suite 0. So all the security suites are supported by the simulator. You can change it according to your requirement in the meter template.
All right, great. So there's a question with regards to the hosting. So is the simulator available on AWS? I think that you had mentioned that it is indeed available. As an extension, is it available on any other cloud, or for now it's only on AWS?
Currently, it is supported on AWS cloud platform. But according to your requirement, we can modify it to work on different platforms as well.
All right, all right. Another question is, yeah, so with regards to generating large scale, like so millions of meters, so what would be the typical load, or can we leave it and run for say a week? So those are some of the questions that the person had with regards to large scale meter deployment.
Yes, yes, we can. We can continuously run it for the duration that you require. It can be for weeks, it can be for months. That wouldn't be a problem.
Got it. Yeah, we just got one more question right now. Does the simulator support master and slave combination? Can we configure it?
We can configure only the server implementations using the simulator or the meter implementations from the simulator.
Hmm, understood. Okay. I think that's about it. Let me just go through the questions. Yeah, I think
Sure.
there was one more, actually, a couple of them. Does it support TCP and UDP? And the other one was, can I use IPv6 addressing?
Yes, it offers support for TCP, UDP as well as HDLC. In the initial stage of adding meter template, you can choose the communication profile according to your requirement. You can go with TCP, UDP or HDLC. As well as IPv6 addressing and IPv4 addressing is also supported for both push communication as well as pole communication. It can be applied according to your requirement.
All right. And IPv6, I think that's also something we have. I remember seeing it in one of the options. Right. All right. Yeah, I think that's about it. I think we have hopefully answered all your queries. If not, we will definitely will reach out to you, and we will try to address them as well. Great. So thank you so much once again for this in a very comprehensive session, Aparna, and of course, for all the participants, for all the attendees. I hope it has been quite an informative session. As always, we will be sharing a recording of this webinar in a couple of days, and there will be also be an e-certificate which will be shared as a participation confirmation for this particular session. All right. Thank you so much
Thank
once again. Yeah.
Yes, thank you. Thank you all for attending the webinar. We hope the session has been helpful for you. Thank you. Thank you very much.
Take care. Have a good day, everyone.